Hello and welcome to the next lecture in our IP Multicast lecture series. The topic for today is Advanced PIM Sparse Mode. In our last lecture, Lecture 7, we introduced PIM Sparse Mode. We went over all of the concepts that are basic to PIM Sparse Mode, that are essential to it. We went through first hop router signaling, we went through last hop router signaling, and most importantly, we introduced the concept of rendezvous point and how it brings together these last hop and the first hop routers together. For this particular lecture, we are not going to go over all of those basics. So there is a bit of a prerequisite before you go into this lecture. And that is you either already know sparse mode, so you've worked with sparse mode, you've studied sparse mode, you're aware of sparse mode, you know sparse mode, or you've simply watched lecture 7. So if this is the first time that you're ever hearing about PIM Sparse Mode, this is your first lecture, the first educational endeavor on PIM Sparse Mode, then I think frankly you will be lost going through this particular lecture. So either you're already trained in PIM Sparse Mode and you just want to build on top of it, you want to take a deep dive into it, or you've watched lecture 7. So this particular lecture though is also broken into two separate parts, and that's to keep the length manageable. Both of these topics are pretty dense and we really need to go in depth, and I couldn't justify creating a lecture that was about 2 hours long, so we're breaking it down into two parts. In part 1, we will be covering all of the join Prune based signaling that is applicable to PIM. So all of the join signaling that the rendezvous point does, all of the join signaling that the last hop router does. So really we are just discussing the PIM join Prune message in a lot of detail. In part 2 of this, we'll actually take a look at the source registration. So really the first hop router signaling. Having said that, let's begin with our lecture for today. Now, the very first process that happens in PIM Sparse Mode is the same as PIM Dense Mode, and that is the neighbor discovery and building up of the neighbor adjacencies. This is required to create what is called the base multicast tree. Now, this is the topology of links where the multicast traffic can actually flow. So wherever the PIM neighbors discover each other, and this is all at layer 2, the routed multicast traffic facilitated by PIM can only flow over that particular topology of links. So the routed multicast traffic only flows between the two directly connected PIM neighbors and almost nowhere else until you're using something more fancy or something more arcane. At times, especially in the JNCIE lab or the CCIE lab, this particular topology, this multicast topology, could be radically different than the unicast routing topology. If you look back at our earlier PIM lectures, you will realize that PIM essentially uses this unicast topology or routing topology information to really build its own routing databases, because PIM doesn't really exchange any routing information, only signaling, and it uses the unicast routing topology and the unicast routing table information. When the multicast table is different from the unicast routing table, that leads to some interesting problems, and that essentially means that you, as the IP multicast network engineer, have to come over some challenges to make sure that the multicast traffic flows properly, and the information that we are bringing over from the unicast routing topology is overridden in some way, or we are ignoring some of the information. Makes life interesting. For the most part, in production networks, the unicast routing topology should be identical to the multicast routing topology and really should not be any difference there. So troubleshooting wise, it's probably a little bit easier in the production network. But because of some corner case, you cannot activate multicast on certain link, but unicast is still working there. That's where you have to use some overriding mechanisms of PIM that are available in PIM, or use some different topology information to build the trees properly. Now, how does this neighbor discovery actually take place? So this is pretty simple. It uses hello messages, and those hello messages allow the PIM routers to discover directly connected neighbors. Again, directly connected meaning connected at layer 2. They share an IP subnet. The hello message itself is just a PIM message, so essentially it's just an IP message. There is the source IP, which is not mentioned here, but the source IP is just the IP of the exit interface. So whatever IP is assigned to the exit interface of the router, that is used as the source IP. The destination IP by now should start looking a little bit familiar. This is 224.0.0.13, or the well-known IP for all PIM routers. So all of the PIM routers are listening to this, and all of the PIM routers send essentially to this IP. The IP protocol contained in the IP packet is 103. That is the well-known number for PIM. So they should be listening to that. On top of just making sure that this particular destination multicast IP is a linked local IP, there is a further security mechanism here, which means that the TTL would be 1. So the message can never actually transit a hop. It's only would be processed by the directly connected neighbors. So TTL01 determines that. There are also several options that are carried in the hello packets, which we will be discussing soon, but these are all contained, or they're carried as TLVs, or type length value fields. So it's very scalable, and you can add more options and you can ignore some options. So for backwards compatibility, this is really, really good to introduce new features. TLV is a very scalable way of doing that. The last thing to mention here, there is nothing in the hello message that identifies the type of PIM process that is working on that link. So essentially there is no validation, or there is no identification for whether that particular interface where the hello message left out of is a PIM sparse mode interface or a PIM dense mode interface. So subsequently, the PIM sparse mode routers can become adjacent with PIM dense mode routers, but the signaling and the mechanisms are so different that your topology at that point would be badly broken. So it is up to you, again, as the IP Multicast network engineer, to make sure that only sparse mode routers are becoming adjacent with sparse mode routers, and also for dense mode routers, the same thing applies. Here is the actual packet format for the hello messages. As usual, the very top 4 fields, the PIM version, the PIM type, the reserved, and the checksum, they don't really need any explanation. We've seen them in multiple messages by this point. Just to make sure that we are covering some of the basic things, the version here is version 2. So PIM version 2 is the overwhelming favorite out there, and you should be used for most types of implementations. The type of the message, or the type contained in the packet format, identifies the message carried therein, and the type for the hello message is type 0. Now there are some relevant options. There are many options that are available with the hello messages. I'll be covering the ones that I feel are important to our lecture series here. So the very first one here is the hold time. So this is how long you're going to wait for a neighbor that is no longer, or that you're no longer receiving any hello messages for. So if the hello messages are going out every 30 seconds or so, and then the hold time carried in that hello packet is about, I don't know, 3 times that value. I'm very bad with the default, so I don't really remember that. But suppose it is, I don't know, 90 seconds. So that is how long you will wait to hear for another hello message before declaring that neighbor dead. This is the same concept as the OSPF dead timer or the EIGRP hold timer. So there's really not much to say here. But again, you will honor the advertised hold time from your neighbor, and you will use that as the hold time for that particular neighbor. The next field here is the DR priority. Now once again, I don't really remember the upper limit or the number of bytes, but higher DR priority would allow a neighbor to overwhelm the other neighbors and become a DR on that segment. We have another complete slide on how the PIM designated router actually works, but this is the field that carries that priority. So we will shelve that discussion till that slide. The last thing here to be aware of is something called the generation ID. This is option 20, generation ID. And this is to basically handle graceful restarts. So anytime a device reloads gracefully, that means the forwarding plane wasn't broken, but the control plane, maybe a supervisor switchover had to take place, or you just had to restart the PIM process on a device. This is the field that will handle those to allow you to do a graceful restart on the PIM process. And what happens is, in case of a soup switchover or a PIM process restart, the next time the particular neighbor that went through the restart will generate a hello packet, it will have a new generation ID. So it's a pretty long string, so there would be a unique generation ID that would be used after that restart. And when the neighbors receive this new hello packet with a new generation ID, that indicates to them that the router that they're receiving the hello from just underwent a graceful restart, so the forwarding plane wasn't killed. And what they would do is they would respond by refreshing or sending all of the S, G or the star, and the star, G signaling on the RPF interface that the neighbor is on. So all of the S, G or the star, G states that have the RPF interface that faces that neighbor, they will all be refreshed. So those states would go out in PIM messages back to the neighbor. So you're back feeding the neighbor with that information to basically bring their PIM database back up to date. So there is more content available on generation ID, but there's really not much. As long as you're doing graceful restart, that's really all you need to worry about when it comes to graceful restart or generation ID. The next topic here is the PIM designated router and how it pertains to sparse mode. So to rewind ourselves a little bit, if you think back to the PIM dense mode lecture, the PIM dense mode also had the concept of a designated router on multi-access interfaces, so Ethernet interfaces, but there was really no need for that particular mechanism, the designated router mechanism, in dense mode. So dense mode itself had no requirement for PIM designated router. Everything was handled using different mechanisms. Why PIM dense mode was doing it was for the sake of IGMP version 1. So IGMP version 1 doesn't have a designated querier mechanism, and it really uses the designated router selected by the multicast routing protocol, in this case PIM, to elect its own queriers. So that's why PIM dense mode needed a designated router, not for the sake of PIM dense mode, but for the sake of IGMP version 1. In PIM sparse mode, designated router election is an actual requirement. So you really need it to satisfy some of the mechanisms of PIM sparse mode itself. So it actually is quite relevant in PIM sparse mode, which it really wasn't in PIM dense mode. Once you elected it, you supplied that information to IGMP version 1 and you promptly forgot about it. There are two main functions that depend on the placement of the designated router. So segments that have multicast senders, so these are the first hop router segments, so multicast senders. The DR, or the designated router, is responsible for sending the PIM register messages. So imagine if there are several routers that are on that first hop segment. Each and every one of them will receive the multicast source signaling. I'm making quotation marks with my fingers. So essentially they receive multicast data packets from a certain source. Imagine if every single one of them was to send a register message to the RP. It would be redundant, it would really confuse the RP, and really the RP wouldn't be able to choose who is the actual first hop router segment. So to basically curtail the number of register messages, you pick one PIM router per first hop router segment to send that PIM register message, and that router ends up being the DR. Now, the segments with the multicast receivers, or the last hop router segments, the DR is similarly responsible for sending that PIM star comma G join message. So the join message has to go towards the RP, and the DR would be, so all of the routers on that last hop segment would be receiving IGMP signaling. Only one out of them, the DR, is responsible for actually converting that IGMP membership report into a PIM join message and then send it towards the RP. So needless to say, the placement of the DR, which router ends up being the DR, it's of utmost importance here, and if you're not looking at the DR, you may miss some of the signaling while troubleshooting or while establishing, and all of the signaling really takes place on the DR. As discussed on the last slide, PIM Sparse Mode, so this should be PIM Sparse Mode, it uses the DR priority option that it's advertised in the hello messages, and there's two things to know. The highest priority is preferred. So whichever PIM router advertises the highest priority automatically becomes the DR on that segment, and all of the other PIM routers on that segment, the so-called non-DRs, will wait for that particular router to perform all of the PIM signaling that needs to be done for that particular segment. If, and by default this is true, all of the priorities match, so all of the routers have a default priority, so you would have if you don't change this manually, you would have a tie on the highest priority. In that case, the highest IP out of all of the routers is used for tiebreakers. So if everybody's priority on that last hop segment or the first hop segment is exactly the same, then the highest IP'd router, that router with the highest IP on that segment, then becomes the DR. And that's all there is to know about the DR. So in our particular topology, if you look at the last hop segment, now that is R5 and R6, in our particular topology, you see that there are two PIM neighbors, or there are two PIM routers that can carry the PIM signaling from this last hop segment. Now, out of these two routers, suppose for whatever reason, whether it was priority or whether it was the IP address, R6 actually ends up winning. So R6 now becomes the DR, and all of the signaling, so if you look at R5 and R6, they are both carrying the signaling for IGMP. So the star comma G that you see here, the star comma G that is here, this is all due to IGMP signaling. So both of the routers have the IGMP signaling, but from this point on, R5 will not process any of the PIM messages. So it will not create any PIM signaling back towards the RP, and all of that particular part of the job will befall R6. So from this point on, if you're aware that R6 is the DR on this particular segment, then all you need to worry about is the actual signaling or the actual PIM states on the DR. You can safely ignore R5 for the most part. Well, that brings us to the actual PIM mechanisms available in sparse mode, and really the most important PIM message in both sparse mode and dense mode, really. But right now we're discussing sparse mode, so it's one of the most important messages in sparse mode. For those of us who listen to the PIM dense mode lecture or who are familiar with PIM dense mode, yes, this is the same exact message that is used for join prunes, or really prunes in PIM dense mode, and also for graft. So really, if you have that knowledge, you're going to find this quite redundant and pretty easy. This one single message called the join prune message, it is capable of signaling both the joins. So if you want to join a particular state or tree, then it's capable of signaling that join, and it is also capable of pruning yourself off a tree that you're already on. So the same message can contain different parts of that same information, and you can either signal a join to a particular state or a prune from a particular state. Furthermore, There can be S, G joins and S, G prunes, and this message is capable of signaling both of them. So you don't need separate messages for S, G joins versus star, G joins or prunes. You use the same exact message. There are different mechanisms available in the same message that allow you to signal both and distinguish both of them. The message itself looks pretty complex. The first time you look at it, yes, it's a very long message and it looks pretty complex. But when you break it down, as you normally have to do with these things, there is something much simpler. So ultimately, you're just signaling states, right? So it could be S, G states or star, G states. So signaling those states is something much simpler. So really break down these messages when you're looking at them. Now, just like hello messages, join messages are processed hop by hop. So from one hop to another, they would be processed by every PIM router that receives them. So some of the things that they share with the hello message is the source IP. So the exit interface's IP is the same source IP. The destination IP is that all PIM routers well-known multicast. So 224.0.0.13, that link local multicast, is the same destination IP for the PIM Join messages. The IP protocol is 103. You should be pretty familiar with that by now. And the TTL is 1. So TTL is 1. That means that the message itself cannot be relayed. So if a router receives a message from a downstream neighbor, it cannot really just simply relay that message to its upstream neighbor. It has to create its own join message. And you will see why relaying it wouldn't be worthwhile anyway. So that TTL01 makes sure that the message is absorbed by the receiving PIM router, and then that PIM router creates a brand new message of its own containing similar information, yes, but a brand new message, and then sends it further upstream. The packet format is, like I said, complex enough where it does need a new slide. So here's the packet format for the PIM Join Prune message. Now all of these packets, I've further broken it down into, say, an orange field and a navy blue field. So the orange field is a common header that is shared by all of the packets. So all of the packets will have this common message or these common fields. So the first thing here is the upstream router. Or really, if you think about it, this is the RPF neighbor. So the very first thing that you need to worry about is the upstream neighbor address. Really, this is just the RPF neighbor for that particular source. So again, remember the message itself is going to be an S, G type message. Yes, there is that star, G part that we will be discussing soon. But there would be an RPF check for the RP there, right? So ultimately, there is an upstream neighbor for both of the states. For S, G, this would be the upstream or the RPF neighbor for the S. For star, G, the upstream neighbor would be for the actual rendezvous point or the RP. So ultimately, you determine that RPF neighbor and you populate this field, the upstream neighbor address field, with that particular neighbor's IP. Now the next thing is the number of groups. So you have to identify how many groups are you signaling. So the whole message is based on the number of groups. So first you identify how many groups, and then you would carry information about those groups. So the number of groups will determine how many groups are in this navy blue field here. So that number of groups could be 1, that number of groups could be 10. But ultimately that would determine how big this navy blue field is. Because once you're done with that first common header, that is followed by n number of instances of the groups. So if you have said that there are n groups carried therein, then you would have information about n number of groups. These are the actual multicast groups that are being signaled. So these are all of the streams that you want to join. Now you may want to join S, G streams or R, star, G streams, but these are all of the multicast groups you're interested in. So all of those multicast groups really would be carried individually. So I'm only showing one of those here. So if you think about it, for my particular packet format that you see here, this N is really equal to 1 because all I'm carrying is a single multicast group address. If you want to think of the scalability of this, so suppose this number was 3, you would essentially see 3 times the information that is contained in the navy blue field. So you'll have multicast group address 1, then the information about that address, then multicast group address 2, the information about that, and multicast group address 3, and then the information about that. So when we talk about the information, what are we talking about? What information? So you, for that particular group, the particular router that is signaling or sending the join prune message, it is either going to join a number of sources. So it could join one source or it could join 10. So once again, that's where the scalability comes in. And that number is populated here. So for my particular case, I'm basically signaling J number of messages, right? So J number of sources. So that means there are J sources contained therein. And each one of these is a separate IP. So suppose you want to join 3 different sources, you would have 1, 2, and 3 IPs here. Now these IPs are really not, it's just not a 32-bit field. It's really a little bit more than that. So it's called the encoded source format, and we'll be discussing it shortly. Essentially, this is the part where you distinguish the S, G from the star, G. But just hold on to that thought for a second, and we'll come to that soon. Similarly, there are a number of prune sources. So I shouldn't have to explain that. These are the sources from whom the stream is no longer desired. So simply, once again, if there were 3 prune sources, then you would have 1, 2, and 3 addresses here. So really, when you break it down, there are a number of groups. So N number of groups, and for each one of those groups, there may be up to J number of sources and P number of prunes. And then you keep on reading the fields as normal. So that is how this message is really quite scalable. That brings us to the simpler of the 2 messages, which is the S, G join. Now, there is a prerequisite for the S, G join, and that is, if you said that the source must be known, you're absolutely correct. So for all of the S, Gs, you must really know the source that you need to receive the stream from. Fortunately, our RP has that information after the source registration has taken place, right? So after the source registration, the RP knows about this information. And really, in our case today, in this particular lecture, the part 1, we'll only see the RP ever creating this message because the RP is the only one who is aware of an actual source in there. So the RP will use this message to create an SPT, or a shortest path tree, towards the FHR. The upstream neighbor, once again, this is the, now I can actually be a little bit more explicit about it. This is the RPF neighbor towards that S. So you do a show IP route, or you would whatever, find the next hop for that source unicast IP address, and that becomes your upstream neighbor, or the RPF neighbor, and you simply populate this upstream neighbor address field with that RPF neighbor's IP. That's it. It's pretty simple now, right, when you look at it. The multicast group is the desired group's IP. So this would be an actual multicast IP, 224.0.0 something or 239.1.1 something, whatever have you in there, whatever stream that you want to join. The joined source, so this particular information is going in here. This is the actual multicast group IP. The joined source is the discovered source's IP. So this is the source that was registered to the RP. So the FHR sends that register message. That register message has a G. So if you think about it, this is that G, and this is the S. And together they form the S, G. And the G populates the multicast group address field. The S then is reflected in this join source field. So you would have a number of join sources, at least one, right? So you're joining at least one. And then that join source address would be the S. Once again, each middle hop router, remember the join messages or the join prune messages really are processed hop by every router that receives them. So every middle hop router will perform an RPF check on that message. It'll process the packet. And although I say that it relays it to the RPF neighbor, so it relays it on the RPF interface towards the first hop router because the journey of the packet must continue, you have to realize that when I'm saying relay, it's actually a brand new message, because for the very first part, the upstream neighbor address would be different for each MHR, each middle hop router. For that particular source, the upstream neighbor address is going to be different. It's going to be the upstream neighbor. So really, it's not a relaying process. I shouldn't be saying that. It's really a brand new PIM join prune packet that is created on the middle hop router and sent towards the RPF neighbor on the RPF interface. So RPF neighbor on the RPF interface is very important. Every middle hop router that receives this message, it'll also create that S, G state. So that's another part of PIM. So you create the state, then you create another packet and you send it further upstream. So creating that S, G state means that you're populating the incoming interface and also you're updating the outgoing interface list or the OIL. Finally, the message should reach the LHR, and the LHR should then join the receiving interface to the OIL of its S, G state. So here is the RP actually joining the S, G tree. So we have skipped some essential steps here. So if you look at lecture 7, you would see all of those steps in there. But right now, there are a couple of things that must be noted about this particular topology. So for the very first thing, there is a PIM registration message. So if you look at that yellow message, that PIM registration message has already been sent from the first hop router R1 to the rendezvous point, which is R3. So R3 is already aware of an S, G state. Also, the last hop router R6 has shown its desire to join that group. So the star, G join has already reached the RP, and the RP has an S, G state and a star, G state. So now it can create, or it can place itself on that S, G tree using this S, G join prune message. So what it does really is it sends that message to R2. Because R2 happens to be, for this source S, R2 really happens to be the RPF neighbor. So before doing that though, R3 will be doing two things, right? So the R3 router would take this interface, the outgoing interface, and it will treat that interface as the IIF for that S, G state. So that's very important. In the S, G state, you identify the IIF, and that is the RPF interface for the S, and you, or R3, really reflects that as the IIF for the S, G state. When R2 receives this message, it is going to do two things. It's going to create an S, G state of its own. So once it creates the S, G state, it is also going to update that S, G state with the outgoing interface list, or it'll create an outgoing interface list for that particular state, and it will add that receiving interface, the interface between R2 and R3, to the OIL. So if it's the only interface, then it becomes the OIL. If it is an additional interface, then it is added to the OIL. But whichever way you do it, that's what is going to happen. R2 is also going to identify the RPF interface. So in this case, that RPF interface happens to be this interface between R1 and R2, and it is going to identify that interface as the IIF for the S, G. And once all of that is done, the S, G state on R2 is quite complete, and it can then send the S, G join prune message to R1. Now R1 already has an S, G. The S, G state in R1 is really because of the source signaling. So it's receiving the multicast feed, and that is what's keeping that S, G state alive. So for R1, there was already a IIF. And this is because it's actually receiving the actual traffic on that interface. So it has that IIF, and let me just once again make the colors consistent here. So IIF on R1 is already present because it's receiving the traffic. What it is going to do in response to that join prune message is R1 is actually going to add this receiving interface into the oil. So it updates the oil with that interface, and now the SPT signaling between RP and the FHR is quite complete, and you can R1 can actually start sending the multicast messages, or the multicast traffic. The actual traffic that is received by R1 from the source can now be sent down the tree to R2 and then towards R3. So this is the S, G signaling's final goal, and as you can see, it has met it here. The star, G message is slightly more complex than the S, G message. But all of the things that we discussed in the S, G message also pertains to the star, G message. There are a few additional things. Essentially, remember when we talked about the joint source address, the encoded source format? We'll be discussing a little bit of that encoded source format, which will then carry the information basically distinguishing the S, G message from the star, G message. Once again, this is used by the last hop router to signal the RP. The upstream neighbor here. So as with the S, G message, as with the star, G message, this most important field of the upstream neighbor address must be populated. And in here, it just happens to be the RP's IP. So you'll take the RP's IP, and this would be the RPF neighbor for that RP's IP. So really not the RP's IP that is populating this field. This is the RPF neighbor for the RP's IP. The multicast group is the desired group's IP. So this really doesn't change. This is that G that we talked about. But the join source now happens to be the RP's actual IP address. So suppose, once again, skipping through the number of join sources, suppose this was 1. Then this address here is the RP's IP. So RP's actual IP address populates the join source address field. Now really the join source address field, like I said, it's not just a 32-byte field. It really is this particular field here. So there's an address family there, there's an encoding type here, and there are some other things in addition to the source address. So to populate this field, the RP's IP would populate the source address field. The address family then happens to be IPv4. Forgetting about the other things, there are 3 specific flags in here. These 3 flags are just single bits, and when they are set, they are 1. When they are unset, they happen to be 0. The 2 flags that are going to be set for an S, G message, and really those flags distinguish the S, G message from the star, G message, are the wildcard flag. So the W flag there is going to be set to a 1, and this indicates the asterisk or the wildcard as the source address. The second flag that would be set is the R flag, and this indicates that the source IP field contains the RP's IP. So really by populating or by setting both of these flags to 1 or both of these fields to 1, Now, the receiving router can distinguish an S, G message from a star, G message, wherein if these two flags are set, it becomes a star, G message. All of the star, G messages will always have both of these fields set to A1. So it will be a wildcard join because it's a star, G join. It'll also have the RPT flag there, indicating that it is trying to join the RPT, the rendezvous point tree, and not the SPT, the shortest path tree, and that the source IP address contained herein is the RP's IP. So both of those flags must be set, must be equal to 1 for all of the star, G message. For the middle hop routers, this is really easy. Repeat the process. The middle hop router will perform an RPF check, process the packet, create the star, G field, and then once again I use a bad term here, it's said relays, but now you know that it'll create a brand new star, G message of its own, and then send it on the RPF interface towards the RPF neighbor for the RP. So hop by hop, you're checking the RPF so you're doing the reverse path forwarding check on the RP's IP. So because of this, all of the middle hop routers must have the same RP information. So they must think that the RP for that group is the same as the sending router. That information has to be consistent. Once again, the IIF and the OIL would be updated. Finally, the message should reach the RP, who also updates its own outgoing interface list and adds that to the star, G state. So it'll create the star, G state. It'll furthermore add the receiving interface, the interface that is receiving the star, G join, to the OIL, or it may be the only interface in the OIL. Here is the whole thing as it happens in motion, so in an actual animation. The star, G join initiates from the actual receiver. So the actual receiver initiates this message using IGMP. So this blue part here, or the light blue part, is really IGMP. And like I said, R5 will not be involved in this at all. So R5, for all intents and purposes, is the silent partner for PIM. So it creates the star, G because of the IGMP, but it realizes that all of the DR duties should be handled by R6, and R5 itself shouldn't have to do anything. So R6, on the reception of this IGMP join, will create the PIM join. So it'll create a star, G, but it will also update the OIL. So that interface where the IGMP join comes in is added to the OIL. Now, the star, G join can go up towards R4. So there's a couple of essential steps that are going to happen here. The very first step here would be to add this interface as the IIF for the star, G. And this interface, by this interface I mean the RPF interface for the RP's IP. So it has the rendezvous point's IP address. It's going to perform an RPF check. That RPF check will result in an RPF interface, number one, and an RPF next hop, which becomes the RPF neighbor's IP. And in this case, it ideally should be R4. R4 will receive this message. Once it receives this message, the next thing it's going to do is create that star, G entry. So it'll update its own multicast routing table with the star, G entry. And in addition to that entry, the receiving interface, which is the R4, R6 interface, it will be added to the OIL, or it will be the only interface in the OIL, but ultimately there is an OIL and that interface is in it. Once all of that is done, it'll then identify the RPF interface for the RP's IP, and whatever that interface happens to be becomes the IIF for the star, G state. Once all of this has been completed on the MHR, which in this case is R4, R4 can now send the star, G message up to the RP, and once it sends up to the RP. The RP number 1 is going to create that star comma G state. And number 2, it's going to add the receiving interface into the OIL of that state. And now, if you look at the RPT tree is complete from the RP to the LHR, or R3 to R4 to R6. And that's the star comma G join, helping the LHR to become alive on the RPT. So creating the RPT and also have the LHR be on that RPT successfully. The second part of this, the S comma G join, we covered it backwards. So now the RP can start the S comma G join process. But really, this is the first part of that process. That brings us to the end of part 1 on the Advanced PIM Sparse Mode lecture. In part 2 of this lecture, we will be talking about the registration process that happens between the first hop router and the RP, and how RP gets that information, and the deep dive into the packet format and all of that other stuff that we didn't cover in lecture 7 or this lecture. Till then, thank you very much for watching this lecture.